grade 11s. We have to carry on with the bonding section that we have started off with yesterday. And we did a new type of bond yesterday. What did we call it?
Coordinate bonds or covalent.
Yeah? Dative covalent. Okay. A coordinate bond or a dative covalent bond. And how does it differ from a normal covalent bond?
Like, for example, H2O will have 3 hydrogen atoms. So the one hydrogen atom doesn't have anything, so then it connects.
Okay. We have that when we have 2 atoms bonding by means of a coordinate bond, the shared electrons are supplied by only one of the components. All right. What do we call that component? It's got a special name. The one that supplies the lone pair of electrons. The ligand. Yes, a ligand. All right. The ligand is the one that supplies the lone pair of electrons. Okay. Now, I've handed out some notes to you at the beginning of the period, and this is the next section that we are going to do. Your book only has a very tiny reference to the shapes of the molecules, and it is actually a very important part of the work. Now, when we started drawing bonding of molecules, for example, if I had hydrogen, I would draw it like that. All right? There's an electron and there's an electron. And the molecule forms a straight line if you drew a line between the nuclei. We will call a molecule like this linear. Linear. All right? All of the diatomic molecules will be linear. Molecules something like hydrogen chloride will also form a linear molecule because there's only 2 atoms, a hydrogen and a chlorine. Yes, usually it will be a linear molecule. Whether we have a double bond in oxygen or a triple bond like in nitrogen, it doesn't matter. It still forms a line. Okay, so the molecular shape then, just very simply linear, it is the first one on your page. Now, in contrast with this, when we would draw a water molecule, we'd always do it like an upside down Mickey Mouse head. Okay? No, then it's wrong. No, it must be drawn like this. There's a special reason for it. Okay? So, a water molecule, we have a hydrogen, and the hydrogen bonding onto oxygen, forming the water molecule. That's the oxygen nucleus. We find that the hydrogen atoms are bonded with a specific angle in relation to each other, and we'll look at the explanation of that in a moment. So, water is an example of an angular molecule. I'm going to do it in the next, or carbon dioxide I'll show you now in a moment. Okay? When we draw carbon dioxide, because that's actually a very good question, how did I draw it? Yes, next to each other. There's the carbon. I'll show you in a moment. I'll answer that question. Okay, oxygen has got 6. There we go. Yes, this oxygen, carbon dioxide molecule is linear. Okay, I'll do the explanation in a moment. Then another type of molecule that we can do would be something like ammonia. Okay, and what happens is when we draw ammonia, now it's very difficult to draw it in 3 dimensions, but in actual fact we have a nitrogen, all right, and then if I could if my hand was the nitrogen atom, the hydrogens form like a tripod foot. Alright? With the 3 hydrogens. It's difficult to draw because it's a flat surface, alright, and the molecules are 3-dimensional. But it's got like a tripod, like a triangular foot. Okay? So the ammonia would be an example of a pyramidal. A pyramidal shape. And we'll have a look at those angles in a moment. The last shape that you should be aware of, yes? Yeah, it's a dotted line into or out of the page. Remember the Lewis and the Bohr structures? With the Lewis we can draw a line. Are you with me? Okay, so that is what they've used on the diagrams there. Alright, now, the next molecular shape that you must be aware of then is something like methane. And here we find we have a carbon atom and 4 hydrogen atoms. But what it does is, if I had 4 fingers and the carbon atom was here at the top, it makes a foot to stand on. We refer to this shape as tetrahedral. Tetra, 4. Makes a, square foot. Alright, tetrahedral. It's a what? Yeah. Well, yes, it's got, I'm sorry, it's not got 4 on the foot. Alright, yes. I'll explain the shape now when we start with that. Okay, now. There's a definite angle to these atoms when they bond. But what influences this angle in relation to that angle in relation to that angle? And why does this make a linear molecule? Alright, now it's got to do with the electron pairs that are available in the outer shells. Alright? If I go and have a look at my linear molecules, we find that there is a repulsion between the electron pairs. Remember I said to you, why do electrons pair off? When we draw them with the... Yes, they spin in opposite directions, and that is what pulls them close together, so they pair off in twos. But one pair has a repulsive effect on another pair. So they don't go bumping into each other because they repel each other. Now we find that the strength of the repulsion between the pairs of electrons can differ. We refer to a pair of electrons that forms a chemical bond as a bonding pair. Alright? And a pair of electrons like that is not involved in a bond, is known as a single pair. Alright? Are you with me? Now, when I have bonding pair repulsion, it is very weak. No, sorry, single pair. Yes, bonding is weak. Sorry, bonding is weak. When I have bonding pair, single pair repulsion, it is slightly, okay? And when I have single pair repulsion, it is, relatively speaking, very strong. Well, here I have a single pair. Okay. And there I have a single pair. And this, oh, undo. No. Yes. Okay. If I have a single pair, now they go separate. There's a single pair and there's a single pair. These two repel each other. All right. So they push away. Yes. So they will push away as far as they can in 3 dimensions. Now, here I have a single pair, a bonding pair. This bonding pair is going to be repelled by 1 single pairs, 2 single pairs, 3 single pairs. But yes, it's weaker. So they will push into one end of the molecule, and that's where it will stay. Do you understand that? But that is easy because we only have 2 atoms.
Okay, now what about that area of the double bond?
Same thing. Over here we find, well, that single pair, they will repel each other equally. Those 2 will repel each other equally, but they will repel the bonding pairs. But once again, the repulsion on that side is equal to the repulsion on this side. Can you see that? Because those 2 bonding pairs repel those 2 single pairs. And the single pair repulsion is the same over there, pushing them away, but they are repelled. The molecule as an equal distribution. All right? Yes. They've got the same number of electrons and the ones that they share. Yes.
The distance of repulsion causes the angle, like the size of the angle.
Yes.
Okay, maar wat by CO2?
Okay, I'm first going to explain this one. It is over here. I'll do them in comparison. Now, when we get to water, here we find we have 1 single pair, 2 single pairs, and we have got 2 bonding pairs. Now, the repulsion between bonding is very weak. So they do push each other away, but not very strongly. And then we find the repulsion between these 2 pairs is very strong. So they push each other away as far as possible. All right? Then we have this pair is going to repel that pair and that pair, and this pair is going to repel that pair and that pair, slightly weaker than what they repel each other, but stronger than what they repel each other, and it pushes the hydrogen atoms down into an angular molecule. Look at carbon dioxide. On the center atom, we have got 2 bonding pairs and 2 bonding pairs. The repulsion between the bonding pairs is equal. On the oxygen, I have single pair that will repel each other as far as possible, but I have single pair bonding pairs that repel equally. The same thing on that side of the molecule. So there's no resulting force pushing them down. If I had a single pair over there, it would have pushed them. But I don't. You understand? And that is why the carbon dioxide molecule is linear.
Okay, so does a bonding pair, even if it's a triple bond, count as 1 bonding?
In a triple bond, there will be 3 bonding pairs. Okay. All right. Let's.
Bonding pairs, do they then attract each other more because they're always next to each other?
Yeah, well, they pair off in general. All the electrons do, whether they're involved in a bond or not. Yeah. That is why they like bonding if they've got 3 open electrons that haven't paired off. Because there's repulsion between them. It's an unstable state. All right. Now, when we're going to have a look at ammonia, just have a look. If I go and draw my nitrogen and my hydrogens, okay, there's nitrogen. How many electrons does nitrogen have? 5. 1, 2, 3, 4, 5. Yeah. Altogether 7, but 5 in the outer shell. All right? So here we have our hydrogen atoms. Now, if you go and compare this to the water molecule, can you see we have 2 single pairs that will repel each other strongly. And then these single pairs, when they are pushed away as far as they can from each other, they repel those. All right. Now, if we look at ammonia, we only have 1 single pair, so we don't have the strong single pair repulsion. Do you agree? We have got a slightly weaker single pair, bonding pair repulsion, and the very weak bonding. So they are going to be pushed down. Yes? If it has something like that, that's like water. Yes, it does. It's going to push them down further. Because I've got 2 sets of pairs repelling it. Yes, water does. Water's got 2 pairs. 3, it's going to push it down stronger because they will repel each other stronger. Then we've got 3 pairs repelling fairly strong. You understand? Okay. We'll go and have a look at the bond angles in a moment. All right. That is why they differ. Because over here the bond angle will be different because we only have 1 single pair repulsion. They should be slightly bigger. Because the force pushing them down is slightly smaller. All right. But sometimes because we have 3 and on the other one we only have 2, it also plays a bit of a role. All right. So the next one then that we have to have a look at is methane. Now methane has a carbon bonded onto a hydrogen, and a hydrogen. This is a 3-dimensional molecule. Carbon only has 4 electrons, and hydrogen only has 1 electron. So what do we know? Is there any single pair repulsion? No. We only have bonding pair repulsion, and they are equal in all directions. So they are going to go in 3-dimensional structures as far away from each other as possible. Yes, and that is why, if you look on the diagram when it's drawn, it's got a foot on the bottom, like that, and 1 sticking up there, like that. Now, that is the tetrahedral shape. So look at the notes with the typing on it. Yes, that one. Molecular shape at the top, linear, the diatomic molecules. The bond angle is going to be 180 degrees because that angle there is 180 degrees. That's logical. The next one, angular. Now the specific example is that of water. And the hydrogen-oxygen-hydrogen bond over here, this bond, in other words, that angle is equal to 104.5 degrees. Water, yes. You would be able to extend the theory to something with an identical structure. Okay. Yes, yes. All right. Yes, yes, yes. All right, it doesn't matter in which molecule it is. But bonding, single pair. Single pair is very strong, bonding, very weak, and in between bonding, single pair. All right. Then if you go and have a look at the ammonia molecule, here we find that because we have 3 atoms bonded onto them, the bond angle, and there's only 1 single pair, so it doesn't push them as close. All right? So the angle becomes 107 degrees. And the last one, tetrahedral one, methane, the bond angle is 109.5. I always confuse them. They shouldn't, no. If they do, it can be an unknown compound XY4. Similar formula, it's going to be tetrahedral. All right. Okay. Just a little extension. Water is a polar molecule. It is strongly polar. When we did polar molecules with water, when was that? Grade? Did we do it? Somewhere along the line we did it. 2 reasons. The one reason, lots of single pairs on that side. Alright, strong repulsion. I have a charge of -4 there. These repel each other less strongly, alright, push down on the one side. Now, also, this nucleus and that nucleus has an attraction on these shared electrons. Okay? Oxygen attracts those electrons slightly stronger because it's got a greater positive nuclear charge than what the hydrogen will. Yes. So the whole side of the molecule becomes negative, and this whole side of the molecule has a slight positive charge. Okay? Why can something like methane not be polar? Yes, it's a symmetrical molecule. It's the atoms are distributed equidistant in 3 dimensions. Do you understand? So even though the carbon nucleus will have a stronger attractive force on the shared electrons, it's in all directions, and the molecule can't be polar. Because the moment you have a polar molecule, remember the forces between the particles become stronger. If we go and look at ammonia, here we have ammonia. Can you see that ammonia will be slightly polar? Very slightly. But not as polar as water. All right. Okay, that is the bond angles. Just look at the note. I've tried to sort of explain it because your book doesn't really explain it very well. The question below the molecular shape, why are these bond angles not 90 or 180 degrees as one would expect? The reason is the central atom has electrons in its outer shell grouped together in pairs. Electrons which are shared are known as binding or bonding pairs, while electrons which are not shared form a single or lone pair. The ligand is the one that supplies the single or lone pair. All right. They don't take part in the bond. Then there is a repulsive force between the different pairs of electrons. The repulsion between different pairs differ. Single pair is stronger than single pair, bonding pair. And lastly, bonding pair is the weakest. It will be similar to ammonia. No, there will be. Remember, in water, we've got let me draw water over here by the ammonia one. No, where are we there? If I have H3O, remember, I've got oxygen, I've got one hydrogen and another hydrogen, and then I have another hydrogen sticking on there, but the water molecule has got 1, 2, 3, 4. Do you understand? Okay, very good if you can see it. There we go. So it's going to look like ammonia, if you had to deduce an answer, or apply your knowledge to find an answer. What will the shape be? More or less, what would the size of the angle be? Same as ammonia. No? All right. No, just molecular. Ions form a crystal lattice. All right. Okay. The coordinate bond formation at the bottom. Coordinate bonds are formed when both the shared electrons are supplied by one of the atoms involved in the bond. And there I've given you an example of water forming the hydronium ion. Water is the ligand because it supplies the electrons so that a covalent bond can form between the proton and water. And then ammonia to form the ammonium. And lastly, the coordinate bond formation on a hemoglobin molecule. Yes. Okay. That's good. Yeah. Okay. All right, rather late than never, maar is reg. Okay, then on the next page that I've handed out, it's just a more Well, a three-dimensional diagram of what the shapes look like. The first one, linear, angular, or bent. They show the single pair of electrons as two smaller little bubbles. Can you see that? All right. And then pyramidal and tetrahedral. You can ignore the trigonal pyramidal. Don't worry about that one. Okay. That, I think, is the end of today's lesson. So...
Win free airtime with One Africa TV. Share your comments on the channel. WhatsApp your feedback, name and town to 081 200 6659. One Africa TV. It just gets better.
has got to do with writing balanced chemical equations. The heading in your textbooks there on page 38 is chemical shorthand. Now there's nothing new. If I, for example, have, let's have a neutralization, calcium hydroxide plus hydrochloric, I will get calcium chloride plus water. Now, we can go and add in something called state symbols. Calcium hydroxide is water soluble. Acids are also water soluble. Calcium chloride is also AQ. This was not such a good one. And water is a liquid.
So AQ stands as aquatic.
Aquatic, yes, water soluble. If I, for example, said calcium carbonate, this stuff is a solid, plus we can take hydrochloric acid, which is aqueous. There we go. And we will get calcium chloride, also aqueous, plus water, plus carbon dioxide. Technically at this point, no. Okay. They usually will give an indication. You should know that copper sulfate dissolves in water. You know, the ones that we've worked with. Yes, yes. All right. So we refer to something known as state symbols. Now, the state symbols can indicate solid, liquid, or gas, and water soluble. All right.
So calcium carbonate, is that water soluble?
What? Calcium carbonate is not water soluble, it's a solid.
If you get something that is a solid but is still water soluble, like
There.
so you just leave away the
It's aqueous.
yeah, but you leave away the F for being solid.
Yeah, because it's dissolved in water. All right. We have to balance this equation. When we balance with large numbers in front of the formula. Well, you have to have your formula correct, okay? Now, if we start balancing, 1 calcium